Okay, I want to kind of review a couple ideas that we kind of remember from honors about acids and bases. Now, the acids and bases, we actually use laboratory evidence to learn about acids and bases. And one of the experiments we did was to put cabbage juice into different substances. Okay, and the cabbage juice has something called anthocyanins, which is an acid-base indicator. The other thing we did was to test its conductivity, and this is a little bit of, what is this, ammonia. And we notice what happens here is that these do not light up really brightly. It's kind of hard to tell, but this is a small bulb, and it would be, if it was a strong electrolyte, that would be very bright, and it's not, it's kind of dim. So this would be a weak electrolyte. We want to explain that. Okay, so the evidence here is if we look at the, I found this online, so somebody has tested different products here, and that's kind of nice. And so when we look at this, we say, well, some of these got nice and red, okay, and some of these, I'd say that's a red and that's a pink, so that's acids. Okay, then we have other ones that turn blue, okay, so the baking soda and the sodium carbonate and the NaOH, they turn blue or green or yellow, and those are going to be bases. And then some of them stay purple, okay, and the ones that are purple, okay, are the sodium chloride, the salt and starch, and I'm not sure about this borax. I'm not quite sure what's going on with that. Okay, but we can tell, whether something's an acid or a base by what color it changes with the cabbage juice. Now, we're going to use that for our evidence here about acids and bases, and they don't really expect on the AP test that that, but you should recognize an acid when you see one. If you see HCl, HC2, H3O2, vinegar, you should know that those are acids. Base is a little bit less obvious. Okay, this one's pretty obvious here with the NaOH. Okay, but the sodium carbonate and sodium bicarbonate, those are the ones we're going to be talking about today here. Okay, now, if we go back and say, okay, acids, so acids for the cabbage juice are going to be pink and red, okay, and that would be a test we could do. The neutral substances are purple, and then the bases are blue, but they also come out green and yellow and sometimes blue-green, so there's a lot of variety on those guys. Now, getting to the theoretical definition of what's going on, well, theoretically then, an acid is something that increases the H plus concentration in an aqueous solution. Okay, it increases the H plus ion concentration in an aqueous solution. So Arrhenius had one of the early definitions of acids and bases, and he was really talking about aqueous solutions. So it had increases the H plus. Now, a pretty obvious idea would be like hydrochloric acid. So if I take some hydrochloric acid and dissolve it in water, then we know that splits up almost totally into H plus aqueous and Cl minus aqueous. So, we can see that it's going to put a lot of H pluses into solution, so that's an acid. Okay, a base is something that increases the hydroxide ion concentration. So an example up here would be NaOH. And so NaOH, now when that dissolves in water, so we'd actually probably start with a solid, but when you dissolve it in water, it breaks up into Na plus aqueous and OH minus aqueous. So the idea is that it's going to increase the hydroxide ion concentration, and therefore that's why that is a base. Now, the interesting ones, I think, are the ones where, they don't quite fit our situation. Like way back here, when we were talking about ammonia, ammonia is NH3, and when we tested it, it actually came out to be kind of a blue-green color with the cabbage. So we need to understand what's going on with that. So that in order to help that, we have a different definition, and that's the Bronsted Lowry definition of acids and bases. And what they're saying is that acids are proton donors. Acids are proton donors. Now with our HCl, that's not a problem because here we have HCl. It breaks up and gives off H plus ions and Cl minuses. And H plus is a proton. Okay, and H plus is a proton because remember, a hydrogen atom would be a proton surrounded by an electron, and if we take away that electron, we just got a proton. So an H plus ion is the same thing as a proton. So HCl, that we can say gives off H pluses, but what we have to do now is say, well, we have to give it a chemical to donate to. So we say, well, the HCl reacts with the reacts with the H2O. It donates an H plus to it, so we get H3O plus, and then we have Cl minus. So it's almost the same as what we did before, only we're saying that instead of H plus just floating around by itself, this H plus aqueous means we have a water molecule with an H plus stuck to it, so that's where we get our hydronium ion. So this guy is an acid because it's donating to the water. Okay, now bases, this is a good one. So if we were talking about ammonia, we said ammonia, aqueous ammonia, that is a base. Well, what a base does is this is a proton acceptor. So if I put it with water, it turns out in this case the H plus goes from the water to the NH3, and so what we end up with is NH4 plus, ammonium ion, and then we're left with a hydroxide afterwards. So you can see how now ammonia, even though ammonia doesn't have any hydroxides, if we say a base is something that increases the hydroxide ion concentration, well, sodium hydroxide, obviously, since it has hydroxide, it will increase the hydroxide concentration. But ammonia, even without the hydroxides, built into it, will increase the hydroxide concentration because it is a proton acceptor. It will grab an H off of the water and become NH4 plus, and that will increase the hydroxides because what's left from the water, think of that as H plus and OH minus. If the H plus leaves, then we're left with OH minus. So from this example, we get the definition of a Bronsted Lowry base, proton acceptor, but we can also see that if you follow this reaction, it also follows the Arrhenius base because it's increasing the hydroxide ion concentration, even though it doesn't have any hydroxides. And that's going to be important for us. This is also going to apply, let's say, to bicarbonate. We had sodium bicarbonate, and we also saw carbonate. If we had bicarbonate, HCO3 minus, okay, again, it's going to do the same thing. You put it with water, and then what happens is the H goes over here, so we get H2CO3, some carbonic acid, and we get OH minuses. And the same way, if we had carbonate ions, okay, like sodium carbonate, and put it with water, then again the H can go to the carbonate and make bicarbonate and OH minuses. So in each case we're increasing the hydroxide ion concentration because these guys are all proton acceptors. Now the other piece of evidence here that we were working with has to do with whether something's a strong or weak electrolyte. Now, if we tested something like hydrochloric acid is definitely a strong electrolyte because when you put it into water, it 100% breaks up into H plus and Cl minuses. So since it breaks up 100%, then we get lots and lots of ions, and so if we did this test here, we would get a very bright light bulb. But with vinegar, okay, which we know is acetic acid, then what happens is most of it stays together. So HC2H3O2, it breaks up and forms a little bit of H plus and a little bit of acetate. But it also has a very strong tendency to go back together. So we're going to end up with a situation, an equilibrium. So this will be an equilibrium situation where we have lots of our reactant, it'll be very reactant favored, and our K value is going to be pretty small. And it does break up, so we get H's, so both of these solutions, like HCl and vinegar, are both going to change our cabbage into a pink or red solution, but this one is going to change to H plus and also change back again, and that is going to keep the concentration of H plus pretty low. So it's an acid because it donates H plus. This is a weak acid because it breaks up and goes back together. This is a strong acid because it totally breaks up. And how do we know our strong acids? Because we memorize our strong acids. So HCl, HBr, HI, those kind of things. Now this also applies to our base. So when we saw a minute ago about NH3, okay, NH3 plus water, okay, that will break up to be NH4 plus and OH minus. but that also has a great tendency to go back together. So that's another equilibrium. And so we're not going to have that many ions in solution because of the fact that, it breaks up and goes together, breaks up and goes together. And these do not conduct electricity, whereas these do. So it is pretty dim. We saw that on the first page. It's a weak electrolyte. Now, one that's a little bit confusing is something like sodium bicarbonate. So if I have sodium bicarbonate, that is a weak base. So if I put it with water, then what I get is I get a little bit of H's going over here. So I'm going to have sodium ions. I'm going to have H2CO3. And I'm going to have some hydroxide ions. Okay. But because the sodium breaks up so well, I get lots and lots and lots of sodium ions. So I get a really strong electrolyte, even though it's going to be a weak base. So not every weak base is a weak electrolyte because of the sodium in this case. But that is kind of the rough idea here about acids and bases and the evidence we get from Cabbage and the evidence we get from conductivity. And go ahead and do those problems.